welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 1695, titled Maximum Erasure Value. In this problem, we'll explore how to maximize the sum of a subarray with unique elements. Stick around as we dive into the intuition, approaches, and optimal solution for this exciting challenge. In this problem, you're given an array of positive integers called nums. Your task is to select a subarray from nums such that all the elements in the subarray are unique. Once you select this subarray, you can calculate its score, which is simply the sum of all the elements in that subarray. The goal is to maximize this score. Essentially, we want to find the subarray with the highest sum while ensuring that no element repeats. The input consists of an array of integers where the length of the array can go up to 100,000, and each element in the array is between 1 and 10,000. The output is a single integer, which represents the maximum score you can achieve. Let's look at an example to make this more concrete. Consider the input array nums equals 4, 2, 4, 5, 6. Here, a possible subarray with all unique elements is 2, 4, 5, 6. If we calculate its score by adding the elements together, we get 2 plus 4 plus 5 plus 6, which equals 17. This is the maximum possible score you can achieve with a subarray of unique elements, so the output for this example is 17. Now, let's examine another example. If the input array is nums equals 5, 2, 1, 2, 5, 2, 1, 2, 5, the subarray 5, 2, 1 is a valid choice because all elements in this subarray are unique. The sum of this subarray is 5 plus 2 plus 1, which equals 8. Importantly, no other subarray with unique elements achieves a higher score. Thus, the output here is 8. In the next example, the input is nums equals 1, 1, 1, 1, 1. Since all the elements in the array are the same, the only subarray with unique elements is a single instance of 1. The score of this subarray is simply 1. Therefore, the maximum score you can achieve in this case is 1. This illustrates that when all elements are identical, we can only select one of them to form a subarray. Now, let's consider the constraints and some special cases to better understand the problem. The constraints tell us that the length of the array can be as large as 100,000, and the values of the elements range between 1 and 10,000. This means we need to think about efficient algorithms that can handle large inputs. For edge cases, consider a single element array, such as nums equals 7. Here, the only subarray is the entire array itself, and its score is 7. Another edge case is when all the elements are the same, like nums equals 3, 3, 3, 3. In this case, the best we can do is select a single 3, resulting in a score of 3. Finally, if all the elements are unique, such as nums equals 1, 2, 3, 4, the entire array becomes the optimal subarray, and the score is the sum of all elements, which is 1 plus 2 plus 3 plus 4 equals 10. These examples highlight the range of scenarios you might encounter while solving the problem. To solve the problem of finding the maximum erasure value, we first consider the brute force approach. The intuition behind this method is to generate all possible subarrays from the input array nums. For each subarray, we check if all its elements are unique by using a set. If a subarray passes this uniqueness check, we compute its sum and keep track of the maximum sum encountered across all valid subarrays. However, this approach is computationally expensive. Generating all subarrays requires n² operations, and for each subarray, verifying uniqueness and calculating its sum can take up to n. This results in an overall time complexity of n³. The space complexity is n, because we use a set to store elements of the current subarray. Recognizing this inefficiency, we turn to an optimized strategy using the sliding window technique. The sliding window approach addresses the main drawbacks of the brute force method by dynamically managing the subarray and avoiding redundant computations. Using a hash set, we can ensure that the subarray elements remain unique, while incrementally updating the sum as we adjust the window size. This avoids recalculating the sum from scratch, making the process significantly more efficient. The sliding window approach works through a systematic process. We maintain two pointers, start and end, to define the window boundaries. A hash set is used to keep track of the unique elements currently in the window. To begin, we expand the window by incrementing the end pointer, adding new elements to the hash set, and updating the running sum. If a duplicate element is encountered, we shrink the window by moving the start pointer forward, removing elements from the hash set and adjusting the sum until the duplicate is eliminated. Throughout this process, we continuously update the maximum sum encountered. This approach is highly efficient since each element is added to and removed from the hash set at most once, resulting in an O(n) time complexity. The space complexity remains O(n) due to the hash set. Given its efficiency, the sliding window method is clearly preferable for handling arrays with up to 10 to the power of 5 elements, as required by the problem constraints. When comparing the sliding window approach to the brute force method, the trade-offs are clear. While the sliding window technique requires a deeper understanding of the problem and a more sophisticated implementation, its performance advantages are significant. The brute force method is simple but computationally infeasible for large input sizes due to its O(n)³ time complexity. In contrast, the sliding window approach reduces this to O(n), making it exponentially faster. Both approaches use a hash set, so their space requirements are similar, but the sliding window minimizes redundant operations, resulting in far more efficient use of computational resources. Ultimately, the sliding window method was chosen because it balances time complexity and space usage effectively. By leveraging the problem's constraints, it ensures both correctness and scalability, making it the ideal solution for this challenge. The problem is to find the maximum sum of a subarray where all the elements are unique. Let's begin by examining the brute force approach. Here, we iterate over all possible subarrays using two nested loops. The outer loop determines the start of the subarray, while the inner loop extends the subarray to cover all possible ranges. For each subarray, we use a hash set to check if all elements are unique. If the subarray passes this uniqueness check, we calculate its sum and compare it with the maximum sum we've encountered so far, updating the maximum as needed. However, this approach is inefficient because the nested loops result in a time complexity of O(n)³ due to the repeated checks and computations. To address this inefficiency, we can use an optimized method known as the sliding window approach. This method dynamically adjusts the size of the subarray while maintaining the uniqueness of elements. Let's explore how this works step by step. To implement the sliding window approach, we start by initializing two pointers, start and end, which define the boundaries of the current window. We also set up a hash set called unique_elements to track the unique elements in the window, as well as two variables, current_sum to store the sum of the current window and max_sum to store the maximum sum found. The algorithm begins by expanding the window. Moving the end pointer adds one element at a time to the window. If the new element is not already in unique_elements, we add it to the set, update the current sum by adding the element's value, and then compare the current sum with max_sum, updating the maximum if necessary. However, if the new element is already present in the set, it means there is a duplicate. To remove the duplicate, we shrink the window from the left by moving the start pointer forward, removing elements from unique_elements and subtracting their values from current_sum until the duplicate is resolved. Once the duplicate is handled, the new element is added to the set and the current sum is updated. This process of expanding and shrinking the window continues until the end pointer reaches the end of the array. At the end of the loop, the variable max_sum contains the desired result. The sliding window approach is highly efficient because it ensures that each element is processed at most twice, once when it is added to the window and once when it is removed. This results in an overall time complexity of O(n). The use of a hash set for tracking unique elements is crucial, as it allows for constant time insertions and lookups on average, making the operations within the window very fast. Another key advantage is that the window adjusts dynamically, eliminating the need to recompute sums or check for uniqueness redundantly, as was the case with the brute force method. From a data structure perspective, the hash set is used to maintain uniqueness, while the two pointers start and end define the window's boundaries. Additionally, the current_sum variable keeps track of the sum of elements within the window, and max_sum stores the best result. Together, these components make the algorithm efficient and easy to implement. In terms of space complexity, the hash set may store up to n elements in the worst case, giving an O(n) space requirement. Overall, the sliding window approach is a significant improvement over the brute force method both in terms of runtime and memory usage. Here is the Python implementation of the sliding window approach. We define a function maximum unique subarray that takes an array nums as input. Inside the function, we initialize the start pointer, current_sum, and max_sum to 0. We also create an empty set called unique_elements. Using a for loop, we iterate over the array with the end pointer. If the current element at nums end is already in unique_elements, we enter a while loop to shrink the window from the left. Elements are removed from the set and subtracted from the current_sum until the duplicate is resolved. Once the window is adjusted, the new element is added to unique_elements, the current_sum is updated, and max_sum is recalculated to ensure it holds the highest value. After the loop completes, the function returns max_sum, which is the maximum sum of a subarray with all unique elements. This implementation also handles edge cases effectively. For instance, if the input array is empty, the function returns 0. If all elements are unique, the sum of the entire array is returned. If all elements are duplicates, the result is simply the value of one element. For mixed cases, the algorithm dynamically adjusts the window as needed, ensuring correctness and efficiency regardless of the input configuration. This Python implementation solves LeetCode problem number 1695, maximum erasure value using a sliding window approach. The goal is to find the maximum sum of a subarray such that all elements in the subarray are unique. Here's a step-by-step breakdown of the code. 1. Initialization. A set named scene is used to track unique elements in the current window. We also initialize max_sum to store the maximum sum encountered, current_sum to track the sum of the current subarray, and left as the starting pointer for our sliding window. 2. Iterating through the array. We use a for loop with the right pointer iterating over the indices of the array nums. This pointer marks the end of our current window. 3. Shrinking the window. If nums, right, the current element, is already in scene, it means the current subarray is no longer valid, elements are no longer unique. To resolve this, we shrink the window from the left by removing nums, left, from the set and subtracting its value from current_sum. The left pointer is increment to exclude the duplicate value from the window. For expanding the window, once the duplicate is removed, we add nums, right, to the scene set and include its value in current_sum. 5. Updating the maximum sum. After updating the current window, we compare current_sum with max_sum and update max_sum if the current sum is greater. 6. Returning the result. After iterating through the entire array, we return max_sum, which contains the maximum sum of a subarray with unique elements. ### complexity analysis. Time complexity. The algorithm runs in O(n), because each element is added and removed from the scene set at most once. All operations inside the loop are O(1). Space complexity. The space complexity is O(n) due to the scene set, which may store up to n elements in the worst case. This implementation is efficient and handles edge cases, such as an empty array or an array with identical elements, gracefully. The sliding window approach ensures optimal performance by dynamically adjusting the window size to maintain uniqueness in the subarray. Here, we begin by importing the necessary libraries and defining our solution class. Inside, we implement the maximum unique subarray method, which takes an integer array nums as input. To solve this problem, we use a sliding window approach. First, we create a hash set called scene to keep track of the unique elements in our current window. We also initialize variables, maxsum to store the maximum sum of any subarray with unique elements, currentsum to track the sum of the current window, and left as the left pointer for the sliding window. Now, we iterate over the array using a for loop with the right pointer. At each step, if the current element nums, right, is already in the set, it means we have a duplicate in the window. To fix this, we repeatedly remove elements from the start of the window by updating the scene set, subtracting their value from currentsum, and moving the left pointer forward. This ensures that the window only contains unique elements. Once we resolve any duplicates, we add the current element nums, right, to the scene set and update the currentsum by adding its value. With the updated window, we then calculate the maximum sum encountered so far by comparing the current sum with the previous max sum and storing the larger value. After the loop completes, we return maxSum as the result, which represents the maximum sum of a subarray with unique elements. The entire implementation ensures that we efficiently handle duplicates and maintain the highest possible sum, making this sliding window solution both optimal and easy to understand. To solve this problem, we start by analyzing the array nums equals 4, 2, 4, 5, 6. We initialize several key variables. The scene set will help us track unique elements within the current window. The max_sum variable stores the maximum sum of any unique subarray encountered so far, while current_sum keeps track of the sum of the current window. The left pointer marks the start of the sliding window. Now, we begin iterating through the array with a right pointer. At index 0, the value is 4. Since 4 is not in scene, we add it to the set, update the current_sum to 4, and adjust max_sum to the maximum of 0 and 4, which is 4. Next, at index 1, we encounter the value 2. Similarly, since 2 is not in scene, we add it, update the current_sum to 6, and max_sum becomes 6, as it is greater than the previous value of 4. When the right pointer reaches index 2, the value is 4. This time, 4 is already present in the scene set, which means the window contains duplicates. To address this, we shrink the window from the left by removing nums, 0, which is 4, from scene. This reduces the current_sum to 2, and we increment the left pointer to 1. We then add 4 back to scene, recalculate the current_sum as 6, and max_sum remains 6. Moving to index 3, the value is 5. Since 5 is not in scene, we add it, update the current_sum to 11, and adjust max_sum to 11, as it is greater than the previous value of 6. At index 4, the value is 6, which is also not in scene. We include it in the set, increase the current_sum to 17, and update max_sum to 17, which is the highest sum encountered so far. After iterating through the entire array, the final output for this example is 17. Now, let's explore another example with nums equals 5, 2, 1, 2, 5. As before, we begin by initializing the scene set, max_sum, current_sum, and left pointer. At index 0, the value is 5. Since 5 is not in scene, we add it to the set, update current_sum to 5, and adjust max_sum to 5. This marks the start of our sliding window for this array. Continuing, at index 1, the value is 2. Since it is not in scene, we add it, increase the current_sum to 7, and update max_sum to 7. At index 2, the value is 1. Again, this is a new value, so we add it to scene, update current_sum to 8, and adjust max_sum to 8. At index 3, the value is 2, which is already in scene. This means we need to shrink the window to remove duplicates. We remove nums, 0, which is 5, from scene, reducing current_sum to 3, and move the left pointer to 1. Then, we remove nums, 1, which is 2, further reducing current_sum to 1, and increment left to 2. Finally, we add 2 back to scene, update the current_sum to 3, but max_sum remains 8. At index 4, the value is 5. Since 5 is not in scene, we add it to the set, update the current_sum to 8, and max_sum stays at 8 because it is equal to the current sum. After processing the entire array, the final output for this example is 8. This demonstrates how the sliding window approach effectively handles duplicates while maximizing the sum of unique subarrays. In another example, we examine nums equals 1, 1, 1, 1. Here, all elements are identical, which provides an edge case for our solution. We initialize the same variables, scene, max_sum, current_sum, and left. At index 0, the value is 1. Since it is not in scene, we add it, update the current_sum to 1, and set max_sum to 1. This marks the start of the sliding window for this example. At index 1, we encounter the value 1 again. Since it is already in scene, we remove nums, 0, from the set, reducing current_sum to 0, and increment the left pointer to 1. We then add 1 back to scene, update current_sum to 1, and max_sum remains 1. The same steps repeat for indices 2 and 3, as all elements are identical. Ultimately, the max_sum stays at 1, and the final output for this example is 1. This confirms that the algorithm efficiently handles cases with repeated values, maintaining correctness and optimal performance. The time complexity of our solution is O(n), where n is the length of the input array nums. To understand this, let's break it down. First, the outer loop, which is controlled by the right pointer, iterates through the array once. This means the right pointer moves from the first element to the last, visiting each element exactly once, contributing O(n) to the total time complexity. Next, the inner loop, which is triggered only when a duplicate is found in the current subarray, comes into play. When this happens, the left pointer increments and removes elements from the scene set until the duplicate is eliminated. Importantly, each element is added to the scene set at most once and removed at most once, which means the left pointer operations are also bounded by O(n). Lastly, the operations involving the scene set, such as adding and removing elements, are performed in O(1) time on average due to the efficient hash table implementation behind Python sets. These components together ensure we achieve linear time complexity. When we combine these observations, the total time complexity of the solution is O(n). Now let's consider space complexity. The dominant factor here is the scene set, which is used to store the unique elements within the current subarray. In the worst case, if all elements in the array are distinct, the set will need to hold all n elements, giving us an O(n) space requirement. Besides the scene set, we also use a few variables such as max_sum, current_sum, left, and right. These variables require constant space, or O(1). Therefore, the overall space complexity of the solution is O(n), dominated by the size of the scene set in the worst case. To better understand the efficiency, let's compare this sliding window approach to a brute force method. A naive solution would involve generating all possible subarrays, checking if each subarray contains unique elements, and computing their sums. This approach involves O(n²) subarrays since we generate n subarrays for each starting index, and checking the uniqueness of each subarray takes O(n). This results in an overall time complexity of O(n³), which is highly inefficient. On the other hand, the sliding window approach processes the array with both pointers traversing it at most once, achieving a much better time complexity of O(n), while the space complexity remains O(n), thanks to the scene set. It's clear that the sliding window method is optimal for this problem. Furthermore, analyzing specific scenarios, in the best case where all elements are unique, the while loop never executes, and the algorithm completes in O(n). For arrays with a mix of unique and duplicate elements, the time complexity remains O(n), as both pointers traverse the array. Even in the worst case, where all elements are duplicates, the left pointer still processes each element at most twice, once it's added and once it's removed, keeping the overall complexity O(n). To mathematically validate this O(n) time complexity, consider that the outer loop controlled by the right pointer iterates exactly n times. Additionally, the inner while loop, triggered by duplicates, performs a total of at most n iterations over the entire execution, as each element is added to and removed from the scene set exactly once. Since all operations inside the loops, such as set insertions, deletions, and arithmetic operations, are O(1), the total time complexity sums up to O(n) plus O(n), which simplifies to O(n). Regarding space complexity, the scene set holds at most n elements in the worst case, giving us an O(n) space requirement. Meanwhile, all other variables consume constant space, or O(1). Thus, the overall space complexity of the solution is O(n). This makes our approach both time and space efficient. When solving the maximum erasure value problem, there are several common mistakes to be aware of. One major issue is not handling edge cases properly. For instance, if the input array is empty, contains just one element, or all elements are identical, your solution might fail or produce incorrect results. Overlooking these special cases often leads to runtime errors during testing or interviews because the solution isn't robust. Another common pitfall is relying on inefficient brute force solutions. While these might technically work for small inputs, they quickly become impractical for larger arrays, such as those with 10,000 elements or more. This is because brute force methods typically have a time complexity of O(n³), which is far too slow for competitive coding scenarios. Lastly, errors in implementing the sliding window technique can also cause problems. For example, if you forget to shrink the window correctly upon encountering duplicate elements, it can lead to incorrect results or even infinite loops. It's essential to maintain the balance between expanding and shrinking the window to adhere to the problem's constraints. Another mistake to watch out for is ignoring space complexity. If you use data structures like arrays or sets without considering how much memory they consume, your solution may still be correct but flagged as inefficient during an interview. High space usage can be a red flag, especially in scenarios where optimization is a priority. Additionally, off-by-one errors in subarray bounds are a frequent source of subtle bugs. These occur when start and end indices are calculated improperly, or elements are included or excluded incorrectly. Such issues can produce wrong results that are hard to debug. To improve your approach, remember that interviewers often prioritize optimized solutions over brute force ones. For subarray problems, techniques like sliding window or two-pointer methods are highly favored. Recognizing patterns in the problem, such as constraints involving uniqueness, sums, or lengths, can help you identify the right approach early on. It's also a good idea to discuss trade-offs between time and space complexity when asked about alternative solutions. This shows a deeper understanding of the problem. Lastly, proactively explaining how you plan to handle edge cases before you start coding demonstrates foresight and structured thinking, which are qualities interviewers value. It's also helpful to familiarize yourself with related problems, as they often share similar patterns and techniques. For example, LeetCode 3, longest substring without repeating characters, is a classic problem that involves managing uniqueness within a sliding window. LeetCode 209, minimum size subarray sum, focuses on finding subarrays that meet specific sum constraints and is another great exercise in sliding window implementation. Similarly, LeetCode 424, longest repeating character replacement, and LeetCode 76, minimum window substring, offer challenges that require you to refine your understanding of sliding window and subarray techniques. Practicing these problems will not only strengthen your grasp of the maximum erasure value problem but also prepare you for a range of related interview questions. There are also alternative approaches to solving subarray problems that you might consider, each with its own trade-offs. The sliding window technique is a powerful method that reduces time complexity to O(n) by dynamically adjusting the range of indices. However, you need to carefully manage the window to ensure correctness, which can require extra effort. Hash sets or hash maps are also common tools in these problems, especially for tracking unique elements or counts within the current window. While they offer fast lookups on average, they do introduce additional space complexity. Another option is the prefix sum technique, which can simplify problems involving cumulative sums or differences by pre-computing those values. The trade-off here is the extra memory required for the prefix sum array, and it's not ideal for problems with uniqueness constraints. Finally, for problems that involve finding the maximum or minimum subarray lengths, binary search combined with a validation function can be an effective strategy. However, this approach is more complex to implement and isn't suitable for all scenarios. By understanding these methods and their trade-offs, you'll be better equipped to choose the most appropriate solution for the given problem. Great job on completing this problem. To recap, we used the sliding window approach with a hash set to achieve an optimal solution with O(n) time complexity. Remember, key takeaways include the importance of mastering sliding window techniques and understanding edge case handling. Thank you for watching, and don't forget to like, comment, and subscribe for more problem breakdowns. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!